Thanks a lot to the organizers for inviting me to speak. It's my first time at the Simons Foundation, so I'm very happy to be here. And as we heard, I'm going to talk about prime detecting sieves. And essentially, everything that I'm talking about that's new, at least, is all joint with Kevin Ford. And this is quite a long-running collaboration we have working on this topic. We have one paper out, but we're still sort of working on trying to do more. So part of it is a status report of roughly where we're up to. Part of it is explaining what we've already done and the general problems here. I'm aware that this is a somewhat mixed audience, so I'm certainly hoping that the first half of my talk is maybe accessible to those who don't really work on primes and sieves, even if maybe it's stuff that's well known to experts. And maybe my first task is to try and shoehorn the relevance of what I'm going to talk about to questions to do with probability and universal statistics, which is maybe somewhat tenuous, but the motivating question that I'm interested in for all of this work is maybe the most basic one you could imagine in prime number theory. Given some set A of integers, and let's imagine it's contained in some dyadic interval x up to 2x, how many primes are there? So this is a sort of stupidly general question as it's currently formulated, and there's lots of wiggle room for what kind of questions you might imagine you could ask. So if you just took A to be the set of all integers, this would just be asking how many primes are there of size x. We have a reasonable answer to this given by the prime number theorem, but refined quantitative answers suddenly get close to questions like the Riemann hypothesis. But then lots of the other most famous open problems in prime number theory can also just be phrased in this way. For the twin prime conjecture is essentially equivalent to the claim that when A is the set of shifted primes p plus 2, that there's always at least one prime in the set. And similarly, you could take A to be the set of values of a polynomial, and then you'd be looking at prime values of a polynomial. Ignoring the fact that this is way, way too general for us to possibly hope to have a kind of concrete answer for a general set A, there'll nevertheless be a completely naive guess that you could just imagine taking an integer n between x and 2x uniformly at random, and then we're asking for the coincidence of two different properties, one property being in your set A and the other property being prime. Take n uniform random in x, 2x, then the probability that n is prime is approximately 1 over log x. The probability that n is in A is essentially the size of your set divided by x. And the most naive guess would be that these two properties might be roughly independent on average. And so you might hope that the probability that n is prime and in A is just the product of these two probabilities, at least approximately. So And if this was the case, this would mean that you might guess that the number of primes in your set A should be roughly equal to the size of A divided by log x. Now, it's not difficult to see that this naive guess is way too naive in even lots of very basic examples, that if A only consists of even numbers, there's clearly no primes in A, and these probabilities are very far from independent of one another. And this means that for lots of sets A of interest, we expect this guess, even when we expect there to be lots of primes, to be incorrect. So we expect that this is given the wrong answer for when A is the set of shifted primes or values of, prime values of n squared plus 1 and things like that. And that's all because in the same way that no prime numbers are even, there's a clear codependence between these two probabilities based on divisibility by small integers. Problem, this doesn't take into account the fact primes are odd or not a multiple of 3. So a slightly less naive, but still pretty naive guess. So maybe a refined naive guess is that you could condition on the event that n lies in a certain residue class modulo various small primes. So the probability that n is prime, given that n is congruent to B modulo the maybe product of the first few primes up to Z, would then be, you'd have a correction factor, would be B over, would be the product of primes up to Z divided by essentially the product, the number of possible choices of coprime residue classes times 1 over log x if B is coprime to the product of primes up to Z. And this probability would be equal to 0 if B has a common factor with the product of primes up to Z. And similarly, you can look at the probability that n is in your set A, given that n is congruent to B modulo this product of primes up to Z. And well, the size of this will be A over x times some correction factor, which I'll call beta p. Now, this is going to depend on my set A, and you can easily come up with slightly weird sets A where where maybe this doesn't have a terribly nice formulation, but for the vast majority of sets A that we're interested in, there's a very natural density of elements of A in one of these residue classes. And then the natural guess is that once we've conditioned on looking at integers n with no small prime factors, then these two events should behave as if they're independent. And this would lead to a refined guess that the number of primes in A should be roughly equal to, what have I put here? Maybe this should be some product over primes less than or equal to z. And then there'll be some slightly different densities, beta p tilde, times the size of A, let's be consistent in my notation, divided by log x. And there's one slightly unsatisfying thing about this guess, that I've introduced this parameter z that I haven't really said anything about. And so the left-hand side doesn't depend on z, but the right-hand side does depend on z at first sight. But it turns out that actually this product of densities beta p tilde essentially converges normally very quickly to a constant. And so the natural thing is that actually this product doesn't really depend on the quantity z.
Do you really want that to be independent of b? N is congruent to n in A and congruent to b?
OK, yeah, so maybe for this talk, I'm kind of imagining it's independent of b, provided b's coprime. Here, it's not too difficult to put in some multiplicative factor that does depend on b, but for the purposes of this talk, let's imagine it's independent of b, provided b's coprime to the congruence class. And in fact, in most cases of interest, product p less than or equal to z, beta p tilde tends to a constant as z tends to infinity, so it's therefore essentially independent. So you can just take any z that's going to infinity slowly with x, and this is then the natural guess. And as Andrew mentions, maybe in some cases there should be a small dependence on b here, but you can do exactly the same thing, that this is the conditional dependence, and then we're just summing this over b's. And for almost all of the most famous examples of sets A, we have a concrete conjecture that this is what we expect the main guess to be like, and they all look like the size of A divided by log x times some product of local densities, which is taking account divisibility by small prime factors. So the twin prime conjecture has a quantitative form in this sense, primes of the form n squared plus 1, and lots of the, when we do prove results about primes in sets A, they typically take exactly this form. So it's a famous result, say, of Friedlander and Iwaniec. There's infinitely many primes with form x squared plus y to the 4, and that correct result is given an answer precisely of this shape. And you might guess that there's also concentration of measure type phenomena, so this would hold with a very small error term, but that's starting to get into questions that are going to be way beyond any possible current techniques. But this is my hope at some sort of universality type phenomenon, that we're expecting that actually the number of primes in A should have this fairly universal type formula that just depends on some fairly weak information about the distribution of A in arithmetic progressions. And lots of the most famous problems in analytic number theory and prime number theory are all of this shape. So maybe just to give a couple of examples, you could take A to be the set of primes shifted by 2, maybe interset x to x, and then you're just looking at the density of A in these arithmetic progressions, and you guess the number of primes in A should be equal to 2 times the product over all primes bigger than 2 of 1 minus 2 for P divided by 1 minus 1 over P all squared times the size of A divided by log x, and I guess this is a asymptotic, and this is the quantitative form of the twin prime conjecture. And this infinite product here just converges to a fixed number known as the twin prime constant. And similarly, you could take A being the values of the polynomial n squared plus 1, and then you'd guess that the number of primes in A should be the product of 1 minus 1 over P, then there'll be a plus a Legendre symbol depending on whether minus 1 is a square or not mod P, all divided by 1 minus 1 over P. And again, this converges to a fixed constant, and then times the size of A, which is something like root 2 minus 1 times x to the half at log x. So this is intersect x up to 2x, and you guess. So these are two maybe rather different sets A. They have various different arithmetic properties, but we're saying that all that we think really matters from the purpose of point counting primes in the set A is its distribution in small arithmetic progressions. So A, I've already got P as a prime here. So the size of A is x over log x. And so the size of A divided by log x is x over log x squared.
You're taking that to be a subset, right? A to be a subset of like primes, shifted primes.
So here, yeah. So I'm not sure what the question. So the size of A is of size roughly x over log x because it's shifted primes, and then the expected number of primes should be the size of A divided by log x, which is of size roughly x divided by log x squared. So I think this is the correct formulation. Yeah, I know it's often stated as x divided by log x squared times the twin prime constant. But I'm trying to set things up here so that we're always in a so-called like linear sieving situation. So I guess a very natural question is, given that we seem to have the same sorts of properties for a wide variety of sets A, or at least the same guesses, when does this hold and when does it break down? And clearly you can't really hope to have a reasonable answer to these sorts of questions unless you have some understanding of your sets A, and in particular you're going to need to impose some understanding of your set A in arithmetic progressions for these products of densities to even make sense. So I want to assume a slightly technical property, which is that we understand A in arithmetic progressions. Maybe I'll just assume that we understand A moderately well and arithmetic progressions. And so I'm going to call this property I, and it's going to depend on a parameter gamma. And so I want to look at all moduli going up to x to the power gamma, and I want to say that the number of elements in A, which are a multiple of Q, is roughly A divided by Q. So to make it applicable to all the situations of interest, I want to say that this is essentially A times G of Q for a multiplicative function G with G of P being roughly 1 over P. So maybe I want that maybe that the sum of G of P minus 1 over P has some uniform upper bound A, something like this. But maybe that's a slightly technical thing, and we can just imagine that we have roughly A over Q elements, which are a multiple of Q, for every modulus Q going up to x to the gamma. And so this is a moderate understanding of A in arithmetic progressions, and how quantitatively strong it is measured by this parameter gamma, which I'm thinking of as just a fixed real number between 0 and 1. So smaller gamma means you have weaker understanding of A in arithmetic progressions. Bigger gamma means you have stronger understanding of A in arithmetic progressions. Now I should erase something. So it's then a fact that if A satisfies this 0.1 for some value of gamma between 0 and 1, then you get weak versions of this guess. So for example, you can show that the number of primes in A is bounded above by some constant, depending only on gamma, times the expression that you expected. So this is just a classical result in sieve methods. That you get upper bounds of the correct order of magnitude, and you can get lower bounds if instead of counting primes, you count numbers with no small prime factors. So maybe no prime factors less than x the gamma over 100. You then get that count is lower bounded by something that has the same sort of shape. So we get sort of approximately the correct order of magnitude as a possible upper bound. But the main thing for things like the twin prime conjecture is we'd like a non-trivial lower bound for the count of primes in our set A, and that's difficult. And that's because there can be global obstructions that mean that whether you have primes or not is not just determined by your behavior in small residue classes. However, there can be global obstructions, and so maybe a classic example due to Silberg would be you could consider A1 being the set of P plus 2 such that P has an even number, P has an, the set of P plus 2 such that P plus 2 has an even number of prime factors and A2 being the same thing but with an odd number of prime factors. And we expect that A1 and A2 are going to be indistinguishable from the point of view of the kind of quantitative properties of property 1. That actually we expect that for any gamma less than or equal to 1, both of these two sets will have the right sort of distribution in arithmetic progressions. But clearly, A1 contains no primes, and A2 will contain all the twin primes. And so if you're going to have some general method that genuinely produces primes, you're going to have a method that can distinguish between A1 and A2. And so the okay, yeah. Of course, yeah, we don't really know anything about either A1 or A2. But it's at least expected that they should have a very good distribution in arithmetic progressions. And this is the so-called parity problem about being unable to distinguish between the parity of the number of prime factors based on just understanding the small arithmetic progressions. So the typical way to get around this obstacle is to have some extra arithmetic information about A. You're clearly going to need to put in some extra information, and typically this is sort of some sort of bilinear information. So I want to have given theta and nu with theta and theta plus nu both in 0, 1. I guess they're both greater than or equal to 0. There's a property, so-called type 2 sums, which is some bilinear information, which I want to look at products nm of size x, such that n lies between x to the theta and x to the theta plus nu, and I want to count the number of products nm which lie in A and compare this to the naive probability that a product lies in A, which is the size of A divided by x, and I want to sum it with some bilinear weights, and the hypothesis is that this is bounded above by the size of A divided by some large power of a logarithm for any one-bounded sequences alpha n beta m. So you can think of this as just being a non-trivial bound for the largest eigenvalue of the matrix whose entries are the indicator function that nm is in A minus the expected probability, where the matrix is indexed by n and m. I guess this is not a square matrix because we're thinking of n as being of size between x to theta and x to theta plus nu, so maybe it's the largest single value or something. But yeah, you can think of this as some sort of eigenvalue bound. But the key point is that this property allows you to distinguish between A1 and A2. In principle, because you could think of alpha n as being the indicator function of n being prime and beta n being the indicator function that m is prime, and then this would be essentially getting an estimate for the number of products of 2 primes in your set A. But the fact it has this bilinear structure and it's just an eigenvalue bound means that it's plausible that at least for nice sets A you can actually estimate this. So this is often difficult to estimate, but not completely infeasible in at least some situations. And then it's a fact that if the type 1 holds for gamma and type 2 holds for theta and nu, with gamma plus nu being bigger than 1, then the refined naive guess holds. So maybe I'm suppressing a few slight technicalities, but essentially, if there's this quantitative measure of how big this type 2 window is, which is measured by nu, and there's quantitative information of how well I understand my set in arithmetic progressions, and if the sum of the two lengths is bigger than 1, then I can estimate the number of primes. Henrik? Yeah, an asymptotic for the number. An asymptotic, yeah, with that condition. So morally, this is just Vaughan's identity. Okay, yeah, so that's what the rest of my talk's going to be about. So I'm going to spend like literally the rest of my talk talking about precisely the question that you ask. But this is saying that if you have good understanding in arithmetic progressions and good bilinear understanding, where this is the definition of good, then you get an asymptotic, and this holds essentially for really quite general sets A. But as Henrik mentions, we have this condition for good, and in practice, we can sometimes and quite often establish this for some gamma, some theta, and some nu, but not necessarily quantitatively strong enough that this condition holds. And so a natural question is, to what extent is this condition necessary, either if you're interested in an asymptotic for the number of primes, or if you're just interested in the lower bound of the correct order of magnitude, which is a weaker statement. But you get an asymptotic if the sum of those two lengths is bigger than 1.
Related to so why it might be hard. Suggests the question that does having asymptotics for primes in A apply to?
So maybe not for completely arbitrary sequences alpha n and beta m, but you could restrict to a natural subclass of sequences, and then you get essentially an implication in both directions, I think. So if you had 2 holding just for any one-bounded sequences in this subclass, then you still get the same conclusion, and if you have the conclusion, you can go backwards and get the result for that subclass, I think. But not for completely arbitrary ones. So maybe there's a couple of technicalities that I'm sweeping under the rug, but like at least morally, I think. Okay, I'm a little bit behind time. But yeah, maybe the main motivating question now is gamma plus nu bigger than 1 really necessary? What if we only need lower bounds rather than asymptotics? And also, what are the obstructions? So the dream would be to have a very precise understanding about for what parameters theta, gamma, and nu you had an asymptotic, for which ones you had a lower bound of the right order of magnitude, and also it would be great if we had a very precise description of what the bad sets look like that you would need to distinguish between, because then that would be a natural candidate where you could incorporate some additional arithmetic information to distinguish your set from these bad sets where maybe you don't have primes, but they have very unusual features. And so that's been the main focus of my ongoing project with Kevin. So at least for the asymptotic case, we get a nice, fairly complete answer. Theorem Ford Maynard. For given gamma, theta, and nu, you obtain an asymptotic if and only if you have two conditions holding. So the first condition is that for all integers n bigger than or equal to 1 over 1 minus gamma floor plus 1, there exists an a of n, an integer, such that a of n over n is in theta plus nu, and the second property is that there exists an integer h such that h times 1 minus gamma lies in theta plus nu union 1 minus theta minus nu 1 minus theta. So these are two kind of very concrete arithmetic combinatorial conditions which precisely determine when you have an asymptotic based on your type 1 and type 2 information. So naturally, they're a little bit complicated, but it's not too difficult to see that if gamma plus nu is bigger than 1, these two conditions hold, and so that's consistent. There are various values when gamma plus nu is less than 1, but arbitrarily close to 1, where at least one of these two fails, and so you don't get an asymptotic. But there's also lots of values when gamma plus nu is less than 1, when these two conditions hold. And so concretely, if you have gamma theta nu where these two conditions hold, then you get an asymptotic. If you have gamma theta nu where one of these two conditions fails, then there's an explicit example of a set A which satisfies the type 1 and type 2 assumptions with these parameters that contains no primes. Sorry? Oh, yeah, sorry. Yeah, not that it contains no primes. We're not in that part of the talk yet. It's just where the counter primes is not the naive refined guess, so the asymptotic fails.
You don't control the order of magnitude of it exists on the it's not regular.
So I mean,
I can't read the condition I.
So theta plus nu is some subinterval of 0, 1, and I'm just saying that there has to be some fraction with denominator little n. Yeah. No, yeah, there exists just one an for each n. Yeah, so as soon as little n is bigger than, say, 1 over nu, this will trivially be true. And so in practice, this is just a sort of very short finite check. And it's just checking whether sort of you have a fraction with denominator 5 and a fraction with denominator 6 and a fraction with denominator 7. And for experts, maybe this is morally saying that the Heath-Brown identity is optimal. The Heath-Brown identity is one way of trying to get an asymptotic, is one process of getting an asymptotic for primes, and if these two conditions holds, then you can apply the Heath-Brown identity and you can get an asymptotic for primes. If one of these two conditions fails, then if you try and apply the Heath-Brown identity, you'll get stuck at some point. You getting stuck at some point is actually very closely connected to the whole thing failing, and you getting the wrong asymptotic for primes. And they're being sets with the wrong asymptotic. Okay, so that's given at least a pretty satisfying answer to whether the condition gamma plus nu bigger than 1 is really necessary. No, it's not. This slightly more complicated thing is necessarily insufficient, at least in the absence of any further information. What if we only care about lower bounds? So in practice, there's various kind of fairly messy, complicated sieves, normally based on Harman sieve, that give the world record for lots of things about like the shortest intervals guaranteed to contain primes. And they're normally doing some version of producing a lower bound of the correct order of magnitude for various parameters, gamma, theta, and nu, with gamma plus nu less than 1. Actually, in the most advanced results, there's various extra bits of arithmetic information that go beyond the type 1 and type 2 here, but I'm not going to talk about that today. But in practice, we find that actually, even for remarkably small values of nu, we can often still get non-trivial lower bounds. So in cases where this maybe fails quantitatively by quite a large margin. And so one natural question is, actually maybe for lots of parameters gamma, as soon as you have non-trivial type 2 information, you're ruling out this sort of conspiracy, and maybe you can get primes. That we know that you must have nu being bigger than 0 to possibly get primes, based on the example I put with A1 and A2, the parity problem. But in practice, you can have very small values of nu of size 1 over 30 and still get primes for fairly moderate values of gamma. And we know that if gamma is very close to 1, then actually you only need a very, very tiny bit of type 2 information to distinguish primes. So a second theorem maybe destroys this hope. So given any gamma less than 1, there exists a nu strictly positive such that for theta in 0, 1, there exists a set A satisfying 1 and 2, but containing no primes. So obviously, nu is going to be less than 1 minus gamma, because if nu was bigger than 1 minus gamma, this condition would hold and you'd have an asymptotic. But if nu is small enough, then there's a set A which can have arbitrarily good type 1 information, but just a very narrow bit of type 2 information, and genuinely contains no primes at all. So this maybe dashes any hope based on the numerics that we seem to be able to produce primes even with small values of nu, that maybe just having nu being positive would be satisfactory. Actually, we can have these explicit constructions of sets A, which contain no primes at all, yet satisfy type 1 and type 2 conditions. So we're still working on the process of given gamma, theta, and nu, when can you hope to have a lower bound of the correct order of magnitude and when can you not? There's various good reasons why this is a genuinely complicated question. So the lower bound you get is, it turns out, is discontinuous in various ways. So it has jumps, and sometimes it can jump from you having an asymptotic to suddenly you having no primes at all, just as you vary one of your parameters by an epsilon. Sometimes it can have discontinuities which are just a finite jump. And then in some other regions, it's a sort of smooth continuous function of gamma, theta, and nu, but it's very, very piecewise and messy. And so we're not necessarily expecting there to possibly exist a clean answer as to for which values of gamma, theta, and nu you can get upper bounds and lower bounds, but at least in various common and more simple situations, there are some parameter spaces of gamma, theta, and nu where we can give optimal answers for the upper bounds and lower bounds. So we can say that any set that satisfies type 1 with those parameters gamma, theta, and nu, you have at most this many primes and at least this many primes with some explicit constants, a constant that's bigger than 1 on the upper bound and a constant that's less than 1 on the lower bound times the expected amount. And moreover, we can explicitly construct sets that match that upper bound and that lower bound. For other parameter ranges, we maybe can't prove that the bounds we get are optimal, but we can have a much more general procedure, which is allowing us to get lower bounds of the correct order of magnitude in a bigger space. And we're hoping that there should be, we should be able to produce some underlying computational tool that means that for some, we can at least have a proof that you get a lower bound of the right order of magnitude for a given choice of gamma, theta, nu with only a relatively small amount of computation. And this doesn't require everyone to, in practice so far, everyone has to sort of work very hard to establish their type 1 and type 2 information for their specific set, and then go through some lengthy, messy Harman-Sieve computation for every single thing that no longer really depends on their set at all and is just saying, have I got enough arithmetic information to get this certificate that I have a lower bound of the right order of magnitude? And so we're hoping to have a computational tool that, at least for reasonable values of gamma, theta, and nu, gives a pretty good lower bound and a proof that you get a lower bound of the correct order of magnitude that should cover the vast majority of cases in the literature, and as well as sort of extending lots of the parameter ranges a bit further. And we also expect that there'll be some qualitatively new results because we can show there exist primes in sets that previously we couldn't, because we have this more refined Sieve argument that's optimal in various regimes. I'm almost out of time, but I wanted to maybe just work through a fairly trivial example to give a flavor of some of the ideas that are underlying this. So I want to consider the region where gamma is very close to 1/2. So this actually comes up in various places in practice, and without loss of generality, we can essentially assume that theta plus nu is a subset of 0, maybe up to 1/2 minus epsilon, if this included a range that was a little bit bigger than 1/2, then we could use the type 2 information to extend the type 1 information, so it's the same as the type 1 holding with a bigger value of gamma. So if we're really thinking of gamma genuinely being of size 1/2, we'd expect we can, without loss of generality, imagine that the type 2 information doesn't go over the point 1/2, and then the type 2 information is symmetric in the function x goes to 1 minus x. So if you're avoiding 1/2, then you're either to the left of 1/2 or to the right of 1/2, and if you're to the right of 1/2, you also get the correspondingly reflected interval. So we can reduce down to this case. So first if gamma is less than 1/2, you can consider the set, which I'll call A1, and maybe let this be a random subset of x up to 2x of size x to 0.99, where I'm just picking any element, maybe uniformly at random, with probability 1 over x to 0.01. So this is a set which is going to satisfy my type 1 and type 2 constraints with this value of gamma, just because it looks like the set of all integers. But obviously, this will contain primes. So I want to then take out all the primes in this set. But once I've taken out the primes, I've adjusted the size of the set, and now this is not going to satisfy my type 1 and type 2 information. So I'm going to need to put in some more elements to correct for the distortions caused by removing these primes. And so then I want to add in a random subset of products of 2 primes. And I want them to look like P1, P2, with P1 and P2 both bigger than x to the gamma. And so this is possible because gamma is less than 1/2. I want the size of this set to match the size of the number of primes that I'm removing. So I've then got a different random subset that is still of size x to 0.99. The type 1 constraints only involve moduli going up to x to the gamma, and so never divide primes in here or products of 2 primes in here. So the effect of these two is kind of completely cancelled out. And so this set A1 satisfies the type 1 constraints because it just has the same density. It's essentially indistinguishable from just a random subset of x to x of size x to 0.99. And similarly, it satisfies the type 2 constraints because, again, the type 2 constraints never capture these products of 2 primes or these primes. And so because we're removing some mass and then adding back in an equal amount of mass, and those bits never interact with either the type 1 or the type 2, this set A1 is just indistinguishable from a type 1 and type 2 point of view from a random subset of x up to 2x, but obviously contains no primes. So this means that when gamma is less than 1/2, not only do you not get an asymptotic for the number of primes in a set A, here's an explicit example of a set A that contains no primes whatsoever. And this is consistent with this property because 1 minus gamma here is about 1/2, and essentially no multiple. Well, I guess this quantity fails because it has no fraction with denominator 2. The type 2 interval, theta up to theta plus nu, contains no fraction with denominator 2 when I'm restricting theta and theta plus nu to be away from 1/2. Maybe if I'm being technically correct, maybe this should be a strict interval, I think, to avoid issues near 0. However, one thing that you might notice is that when gamma is very close to 1/2, these pairs of primes have to be very, very close to one another. So somehow we're putting in a very high density of products of 2 primes here. And if instead of A1 being a random subset of x to x of size x to 0.99, I had it of size x over 100, so it was a dense subset, then I wouldn't be able to find enough products of 2 primes to balance the primes here. So this is a very sort of weak proof of principle of the dream I had that if you can understand the counterexamples in a strong way, then you might be able to incorporate some extra arithmetic information into the method and be able to prove stronger results. And so it's a fact that if A is dense, so it has positive density, and then you approach an asymptotic formula for the number of primes in A if gamma sort of tends to 1/2 and maybe theta plus nu either contains or contains 0 1/3, at least in maybe the limit. And so we know that actually for any choice of gamma less than 1/2, gamma being 1/2 minus epsilon, there are examples of sets containing no primes that satisfy the type 1 and type 2. But if you restrict your attention to dense subsets, then such examples can't exist. And in fact, you not only get a non-trivial lower bound for the number of primes in your set, but you approach an asymptotic formula as gamma gets closer and closer to 1/2. So this statement is just a reformulation of work of Duke, Friedlander, of Vanich. OK, I think I'm more or less out of time here, so maybe I'll stop here. Thanks a lot for listening. I'll pass over to questions.
Thank you very much for a beautiful talk. Any questions?
For my remark about condition I misunderstood what you meant. This is property, it's a kind of a different property of the exponents. It's nothing to do with your sequence A.
Yeah.
Please change notation
Okay.
A of n into something else. You know, in Sieves theory, this is yeah. So that's it. No, it's a fantastic work, but extremely complex. You should blame Selberg.
I'm just curious if you have you talked about jumping over these transition points, and obviously you've given us one example. Do you have any other families of examples where you get no primes or fewer primes than you'd expect?
Yeah, so there's lots of different examples. I guess in principle here we've constructed infinitely many examples where you don't get exactly what you expect. And correspondingly there's, I guess here there's infinitely many examples where you don't get any primes at all. But morally they all roughly have this sort of flavor. That I like to think of the constructions as you start out with all integers, then you remove the primes, and then to counteract the fact that you've removed the primes, you typically have to add in some products of 2 primes, Here, this was a slightly artificial example, and it was very easy because it didn't interact with the type 1 and type 2 at all. Typically, it does interact with the type 1, so once you've added in some products of 2 primes, you then have to start taking out products of 3 primes and adding in products of 4 primes and taking out products of 5 primes and doing some sort of jig like this. And all the complexity is then when can you do this in a way that is consistent and the process converges. But that's at least how I morally like to think of it. And so they're all, in some sense, more complicated ideas of this spirit where if you have the wrong number of primes, you also have the wrong number of products of 2 primes with certain exponents and products of 3 primes with certain exponents in various ranges. And how much can you optimize these when you start to have these non-trivial constraints coming from the type 1?
Yeah, I wonder if there's some way to formulate this kind of sieving surgery so that you could make a criteria.
So, I mean, we have it formulated as a sort of functional linear programming problem, and that is kind of equivalent to this process. I'm not convinced that there's any easier way to formulate it than the kind of functional linear programming setup that we have.
Thank you. So I suggest that we keep more questions for the break. We will reconvene at 11, and let's thank James very much again.